Alrighty guys, today we're going to be solving a heat transfer problem involving flow over a flat plate. We have water at 100 degrees Celsius and a velocity of 0.3 meters per second flows over both surfaces of a 0.9 meter long flat plate maintained at 20 degrees Celsius. We're asked to find the water property, the Reynolds number, compute the X critical if turbulent, the velocity and thermal boundary layer thickness, the local heat flux, and the heat transfer per unit width of the plate. First, we're going to start off by getting the temperature film, which is T water plus T surface over 2. We get 333.15 Kelvin, which is 60 degrees Celsius. From table A6 of the Fundamentals of Heat and Mass Transfer, Bergman and Levine, 8th edition, we're going to get density at 983, the viscous forces at 466.32 e to the negative 6. Prandtl is equivalent to 2.9799, and the thermal conductivity is 653.78 e to the negative 3. Starting off with the Reynolds, we're going to use the equation where Reynolds is equal to density times the velocity of the fluid times the length over the viscous forces. From this, we'll get an answer 569,158. That is greater than the Reynolds critical, which is a turbulent flow. Since it is turbulent, we're going to find the Reynolds critical point. By this, we're going to use the Reynolds critical times the viscous forces over the density times the velocity, and we're going to get that the critical point is at 0.791 meters of the flat plate. Now we're going to get the velocity boundary layer. Because it's turbulent, we're going to use the equation where the thickness is equal to 0.37x times Reynolds to the negative 1/5, which is equal to 0.0235 meters. And since it is turbulent, the thermal boundary layer is also equal to that same answer. Now we're going to get the heat flux, where the heat flux is equal to the convection coefficient times T infinity minus T surface. But we don't know the convection coefficient, but we can find this through the equation where convection coefficient equal to Nusselt times thermal conductivity over the length. But since we don't know the Nusselt yet, we're going to have to solve for that. And since it is turbulent, we can find an equation where the Nusselt is equal to 0.0296 Reynolds to the 4/5 power times Prandtl to the 1/3 power. And for the Nusselt, we'll find that the answer is equal to 1712. From there, we can plug that into the convection coefficient equation and get a convection coefficient of 1244 watts per meter squared Kelvin. Then we can plug this back into the heat flux equation. Plugging and chugging, we'll get an answer 99,520 watts per meter squared for the heat flux. And then we're asked for the heat per unit length. And this is just the heat flux times the length. So we're just going to multiply the heat flux times 0.9, which is the length, and we'll get 89,568 watts per meter. If you found this helpful, please leave a like. Thank you.